Okay, so Stable Fluids by Jos Stam. So it's about fluid dynamics for the entertainment business. So that means for movie visual effects, for video games, that kind of thing. Not real science. So why would you want to do this? I mean, in the old days, you used to make movies by actually making models of things and blowing them up and filming it. So a quick anecdote about this. About 20 years ago, when I was still working in the visual effects business, I went down to LA to work on, well, down, it's probably up from here, but anyway, to work on a little bit on a movie called Deep Blue Sea, which probably nobody ever saw. And it has a helicopter blowing up at one point. And it was fun because I'd never been on a pyro shoot before in my life. So we went to watch this model helicopter being exploded, and they pack it full of explosives, and they have the cameras running, and they explode it on video. And then we look at the video, and there's one frame with a helicopter, beautiful, and the next frame, well, there's nothing left. So they'd completely blown it up because they'd packed too much explosive in. So the crew actually have to go around and collect all the pieces off the floor and rebuild the helicopter for the second take, which they did. And if you look on YouTube, you can find this clip listed as like best movie explosion. So it did work in the end, but you can see there's a lack of control, and it's expensive. So computers can do this stuff cheaply. So I thought I'd have a look and see what the earliest example of fluid dynamics in a movie is, computational fluid dynamics. And it turns out to be, I think, this movie, 2010, the sequel to 2001, made in 1984, where they used computational fluid dynamics to simulate the atmosphere of Jupiter. This used the most powerful computer you could buy at the time, just about, the Cray XMP, and this stretched it to its limits. I mean, this simulation didn't fit in memory. They had to figure out some streaming trick to be able to work their way through all of the data. 1999, this paper was published. So, well, this is actually quite a convenient thing. There was a tweet in my stream just a couple of months ago where someone says, let's see, what were the exact words? Arguably the most influential paper in PDEs for graphics, that's partial differential equations, makes CFD, computational fluid dynamics, accessible to almost anyone. So with a tweet like that, an endorsement like that, how could I not talk about this paper, which I already loved? There's another aspect to this. So there was one reply, computational fluid-like dynamics. It's a little bit snarky, but I'll talk about that as well. It's not science, okay? So what do I mean by influential? So I could tell you about the thousands of citations this paper has, but you go to YouTube and type in stable fluids, and you get this endless stream of fluid videos. And these aren't people who've bought some off-the-shelf package. This is the name of the paper that I typed in. These are people who have read the paper. So this contradicts Frank Fenig's talk later, where he said that the classic papers are cited by everyone and read by no one. I think a lot of people actually read this paper. And they went and implemented it for themselves. These are people who've sat down and coded up fluid dynamic solvers for themselves. I mean, this paper enables people to do this. Hundreds of people have done this and posted on YouTube, and I'm sure thousands more haven't posted on YouTube. So that's why I want to talk about this paper. I want you to all write fluid sims, because it's a lot of fun. So this paper took us from, well, so in 1984 we had the sims running on a Cray. Well, in 1999, there was actually a bit of resistance from the SIGGRAPH review committee where this was presented. They felt like there wasn't quite enough original content. I think they wanted just a harder paper to feel like there was some real substance in there. And in fact, even after the paper was published, people were still a bit skeptical because it had been demoed on a high-end silicon graphics machine. And they said, well, you're just throwing computers at it. You can do anything with enough power. So a couple of years later, Jos gave us a live demo on one of these things. Now, I have to explain about this because it looks like a phone, so you think it's super powerful. Okay, this is a 2001 pocket computer. I got one of these for free. I couldn't find any use for it. It's so underpowered. Okay, but I mean, forget GPUs, forget about multi-core. This is just a single-core CPU with no floating point unit. Okay, but he got a real-time demo with his finger. Well, actually, it wasn't his finger. It was a stylus. There was no touch screens back then. So this was actually quite a big advance, even though it's 16 years, to get this stuff running in a fraction of a second for each iteration. So at that point, I think people realized, in retrospect, that this was a good paper. In fact, I tried to dig out a demo from the period. So this is actually Bill Buxton, who was chief scientist at a couple of companies, including Silicon Graphics. So there were touchscreens. They were quite rare. But that's the kind of simulation that people got really excited about in 1999. So, okay, time to start doing some fluid dynamics. There's no escaping it. I think I'm going to have to do some vector calculus. But first, we've got to make a decision. Okay, there's two approaches. I mean, there's others. There's slightly off-the-wall approaches, cellular automata, but there's basically two approaches to fluid dynamics. One called the Eulerian approach, and one called the Lagrangian approach. So the funny thing is, there was an album released by an electronica artist I quite like about a year ago, and it has two tracks on it. One is called a Eulerian description, and another one called a Lagrangian description. And on the album sleeve, except it's download, so it's not a sleeve, is it? But it's actually a complete explanation of what I want, so I might as well just read that. So it says, due to the nature of music, it can be said that there are two ways of perceiving it. The Lagrangian specification, in the Lagrangian specification, the listener may allow themselves to be carried along with the music, as a leaf might be carried along on a stream of water. On the other hand, in the Eulerian specification, it is also possible to perceive the flowing music as a rock might perceive the stream, allowing the water to move around it in a continuously changing flow. Okay, this is actually exactly right, and I'll show you what that means. So, at the end of the day, a fluid dynamic simulation is about a vector field of velocities. That's the key thing that you care about. So, what kind of data structure are you going to use to represent that? Well, you could just store them on a grid. So I hope you can see the vectors. Oh yeah, they do come out. I wasn't sure if the vectors were going to come out on this screen. So you can just store them on a regular grid. So each vector, the base is pinned to a fixed location. The vectors don't move, but the vectors themselves change over time. Nice, easy data structure to work with. It does mess up the mathematics a little bit, and I'll talk about that. And the alternative approach is the Lagrangian approach, where you actually track particles. These are the leaves floating with the water. So you store the velocities just in the particles and don't store anything in between. And this is nice from the point of view of the dynamics, because if you know how to simulate a particle, then you can simulate a fluid. But the problem is that from a data structure perspective, this isn't very nice. The structure keeps changing all the time. Some particles come on, some particles disappear. You can do all that, but we want easy. So we'll go with the Eulerian approach. And now comes some actual vector calculus. Sorry. So I'm going to talk about div and grad, and I bet you thought I was going to say curl, but no, it's the directional derivative. So, quick summary of all this. Here's a map of Hawaii, or a piece of Hawaii, Big Island. Very nice, this area. Colors indicate altitude. Okay, and I've drawn the gradients. The vector gradient. The vector gradient is basically an arrow pointing upwards, and the longer the vector is, the steeper it is. So that's what the gradient of the altitude is at any particular point. It's just that vector. And formally, it's a vector made of the derivatives of our quantity phi with respect to x and y. I mean, literally, this is going back to the roots of what derivative means. The derivative is the gradient. And it works in 2D as well. The gradient is these two derivatives. We're going to also need, by the way, some of this mathematics, there's some pain you have to go through, but some of it's going to disappear away when we get to the actual algorithm. But I think you need to go through the pain to get there. So, and there's a directional derivative. So so we use the funny upside down triangle, del. So del v, what that means is the rate of change of some quantity as you move along the vector v. So if you're driving along in Hawaii and your velocity is v, the rate of change of your altitude is just the dot product between your velocity and the gradient. So if you're perpendicular to the gradient, the dot product's 0, and that means you're following the contours and you're not actually changing altitude. That's why you get 0, and so on. Okay? And there's also a thing called the total derivative. This is really, I mean, imagine you're driving in Hawaii now, but the weather's changing, and we're thinking about the temperature. There are two reasons why the temperature might change in your car. One, because, well, the weather's changing, so that's the first term, the intrinsic change of temperature at a particular place. But also, it's changing because you're driving along, and you might be driving from the beach where it's warm up the mountain where it's cold. So the total change of temperature in your vehicle is going to be a sum of these two terms, the directional derivative and the partial derivative. Actually, mentally I call this thing Big D, but I looked on Wikipedia and it seems to have quite a few different names. I can see why some people might get confused about this subject. In fact, there was more, I didn't do them all. So you can see why I called it Big D. The last thing, divergence. So conceptually, it's a fairly straightforward thing. It basically measures how much stuff's flowing out of any point. So we can draw a little rectangle on a vector field like this. And probably hard to see, but the vectors on the left look like they're a bit bigger than the vectors on the right. So there's kind of a net outflow to the left. So there's a total outflow here. So this is said to have a positive divergence. And we can do this a bit more formally, draw a little rectangle. So basically, in this case, the vectors on the right are bigger than the vectors on the left, so there's a net outflow going right. Well, in the limit, as you make this rectangle small, it's just the horizontal outflow is basically just the derivative in the horizontal direction. And similarly, outflow coming from vertical motion is the derivative the other way. So basically, the total divergence is just the sum of these two derivatives, and that gives you the net flow. So some textbooks will use different notation. I've tried to use the words grad and div so that you can remember. Div is a divergence, sort of outflow, and grad is the familiar notion of gradient. Okay, you know what? Forget this slide. I've got my hand. I can do a demonstration. Okay, so my hand is embedded in the atmosphere here, and the atmosphere has a pressure. Okay, so there's a force on my hand, which is basically just the pressure multiplied by the area of my hand on that side. Okay, but my hand doesn't go to the left because there's also pressure on this side, and there's a force which is that area times pressure. Okay, but if there was more pressure on this side than that side, my hand would actually move unless I resisted it. And again, if you think about my hand in the limit, as my hand becomes infinitesimally small or something, then it's the gradient of the pressure that gives you the force. Okay, and intuitively, you probably know that already. That the force that comes about from a pressure field is minus the gradient of the pressure. It sort of makes intuitive sense. Okay, so now we actually have to do some equations of motion and get the Navier-Stokes equations, the famous equations. So imagine this little square of liquid. This works in 3D, but I'm doing 2D because 3D is harder. So a little square, L by L, area L squared, density rho, its mass is rho L squared. You have to try and look past the rho and L squared. They're just kind of fluff that get in the way a bit, but I have to put them there to be correct. So, and imagine this thing moves under the action of some kind of force. We want to understand the path it takes. So we use good old F equals ma. So in this case, well, the F is just minus the gradient of P. I mean, if this little parcel of fluid has more pressure on the left, it's going to move to the right and vice versa. So that's the force scaled by L squared that I want you to ignore. And then A is acceleration. It's the rate of change of velocity. And we want the rate of change of velocity of this parcel that's moving. So we need the total derivative. Okay, so that's what that dv by dt is. So at the end of the day, we're saying the total derivative of velocity is just minus the gradient of the pressure. And that's pretty much the Navier-Stokes equation. There's a bit missing, but I've expanded out that total derivative. As I said before, it's the sum of two terms, this directional derivative and the partial derivative. So now we've got a step towards an algorithm here. We can rearrange this a little bit. We've got a derivative with respect to time on the left and some stuff on the right. And whenever you have a derivative with respect to time like this, you can do a simulation by basically saying that the value delta t in the future is whatever there currently is, plus the delta t times the rate of change. That's just the standard thing that we use all the time. Okay, but there's some things missing here. I've not said anything about how to calculate this pressure. And okay, to get the coolest looking simulations, you want incompressible flow. So incompressible flow. So if you have some water and you actually put it in a container and try and compress it, it's pretty hard. Water is almost incompressible, at least at normal forces that we experience in our day. And actually, to a good approximation, so's the air as well. Even though you can only hear me because of compression waves, you can still model the air quite well, at least for movie purposes, as an incompressible fluid. So we want to include that. So what do I mean by incompressible? Well, it's just this. So basically what we're saying is that if you have a region of fluid, there's no net change in size of that fluid. So everywhere, there's no net inflow or outflow. So if you have some water in a container and you squeeze it this way, it's going to expand out the other way. So the amount of flow going in is cancelled out by the amount going out. So that's what this is all about. Okay, the divergence of the velocity has to be 0. So I still haven't answered what the pressure is going to be, and it's kind of a strange answer, really. The pressure has to be whatever it needs to be to make sure that the fluid remains incompressible. So basically, you just have to solve these equations. They're simultaneous equations, and that's the Navier-Stokes equations. If you actually know how to solve these analytically, in fact, if you can just prove that there's a solution, there's $1 million prize waiting for you. I mean, these are tough. But we can do it numerically, and we can cheat our way through it, and it turns into something remarkably straightforward. So I just snipped out a piece from Jos Stam's paper. He uses slightly different notation, and there's also this term here, I don't have a laser pointer, which is about viscosity, which I'm going to skip out and not worry about for the moment. I will talk about it later. And there's a force term. If you want to add extra forces to make your simulation do something interesting, well, you can just add that term in as a force, but I don't need to carry it around for most of the work, most of the stuff I'm doing here. So now I need to talk about a thing called advection. So one of the terms in the Navier-Stokes equation was basically looked a bit like this. It's basically the rate of change of velocity is some stuff plus this directional derivative of the velocity. Okay. So this is, if you remember, the directional derivative is basically how something changes as you move along a path. And essentially what this is saying is that this is the equation something would have if that quantity is being dragged along the vector field. So this process of moving a quantity along the field is called advection. So that's kind of an intuitive picture of what this equation is trying to say. So whenever you see this thing going on, you've got to try and think in terms of dragging along the vector field. And so one approach, let's say we just wanted to solve this equation that just does the advection process, forgetting about incompressibility and all that kind of stuff. One way you might try and do this is, well, we've got a rate of change thing. I've talked about that already. You basically take the current value and add delta t times something, okay? And what's the something? Well, you could say, well, we've got a derivative thing here, some expression involving derivatives, so we can get approximate derivatives from a grid just by taking neighboring values, taking the difference, and dividing by the distance between them. That's the standard method we use to get approximate gradients. And that's how you'd compute the gradient of a hill if somebody said, hey, what's the gradient of that hill? You'd pick two spots, take the difference in height, divide by the distance between the points. So we could do that. And then what you'd end up with is a calculation that this something would be some combination of things in the near neighbors. So I'm not going to go through the details because we're not going to do this, but I have to talk about what would happen if you did that. Because there's a kind of flow of information now in your code. The data that's here is getting used over there, but no data from further out is getting used to do this calculation. So now we can say something about how fast the data moves in this code. Well, moves in some abstract sense, right? In some time period delta t, the data moves no further than delta x, which is the spacing between the grids. Okay? Or maybe a root 2 times that if the data can move diagonally. Well, this is a problem, because if the fluid wants to move faster than that, well, if the information about where the fluid is can't move as fast as the fluid is meant to move, your simulation is just not going to work. What happens is fluid starts piling up where it shouldn't because it couldn't move far enough, and you're going to get unstable oscillations coming in. So you basically have a speed limit. So European and American notation for people. So the problem here is one way to fix this is you can make the time step really small, so everything effectively moves really slowly through the simulation. But that's really expensive. You don't want a slow simulation. You want a fast simulation. So this is why we have the name of Stam's paper, Stable Fluids. He has a way of breaking the speed limit without making things go unstable. This is the crucial point. And we do this we made this choice between Eulerian and Lagrangian, but actually we're going to have a kind of compromise here. So here's our grid, and you can imagine that we have some quantity. It could be the velocity, but I'm just going to think abstractly any quantity on a grid, and we've got a value at some point somewhere. What we can actually do is we could imagine each of these grid points is actually a particle, just for a short while, and simulate the motion of a particle. That's actually not too hard a thing to do because you have the velocity stored in a grid, and what you do is you could just do it in one step if you want to do it roughly. You could just take the position of each of these particles and just add the velocity vector, and that gives you a new position. And you could take that as the motion. Or you could do something a bit more detailed where you take multiple small time steps and then interpolate the velocity from the grid points at those intermediate time stages, and then you'll get a curved path. So if you do that, then you could simulate these particles moving. You're going to get something a bit like this. And I've homed in on one of these. So Advection wants to basically transport this value of this quantity from one end to the other. Okay? So you could do that. You've got a value on a grid. You could then transport it to the other end, at the end of this curve, and then put that number back in the grid. But there's a few catches here that it didn't land exactly on a grid point. So what you're going to do, there's loads of ways to deal with that, but none of them are actually all that pleasant. And if multiple particles arrive in the same place, what are you going to do? And if you're doing it on a GPU and multiple particles arrive in the same place, and they all have to write data to the same point, it could be a headache. But there's a really simple trick. Instead of asking the question, where does the fluid at this point here end up, you could ask, at time delta t in the past, what fluid would arrive where I am now? So basically, you just flip the vectors and run it backwards. And then instead of delivering going forwards, you actually collect from the beginning of the path and drag that to the current point now, which is exactly on a grid point. And you can collect from the past easily because you can just do interpolation, even if you didn't land exactly on a grid point. So that was his trick. The funny thing is, this is not his trick at all. This goes back to the 60s, at least for algorithms. And in fact, the method goes back to the 19th century, really. It's basically a method called the method of characteristics. But we can abuse this because, okay, what you're supposed to do is not just drag any old quantity phi, you're supposed to drag the velocity itself along the velocity field. But you can cheat. What you can do is not update the velocity itself. You can use this process and drag the velocity quite a long way along one of these paths. You can go way beyond the speed limit for the Courant condition. In fact, you can go so far beyond that the simulation is inaccurate. But it doesn't matter. You still end up with something that looks kind of like a fluid flow. And what's more, it's stable because you're always just interpolating, which is kind of a weighted average of near neighbors. So you're never going to get a new value of the velocity that's bigger than what you started with. So it never explodes and goes out of control, which can happen with the other kind. So whatever you do, this is a stable simulation. It might not be scientifically accurate, but it's going to be well behaved. And so this was the key thing that allowed him to run his simulations much faster than other people were doing. So I thought I'd give an idea of how some of these flows look. So some people use MATLAB, some people use Mathematica. I like to use ShaderToy. I don't know if you've ever used that. It's basically a nice website you can go to where there's a window on the right where you type in basically a shader, and on the left you get to see the output of that. A shader is basically just a piece of code that's given the coordinates of a pixel and outcomes. You return the color of that pixel. But the cool thing is it runs on a GPU. So this is actually the fastest, easiest way to get into GPU programming. Just go to shadertoy.com. So I thought I'd just do some advection of colors along vectors. Okay, so I'm not doing a full fluid sim. I just want to show the advection thing. So I need to make up some incompressible flows. So, okay, I can use a bit of geometry here. Pick a random pair of vectors, A and K, whose dot product is 0, and then make this function. So basically, that's some kind of wave of velocity. You can imagine the crests of a wave in a row like this, but the amplitude of these waves is perpendicular to the... So if the direction of motion is this way, so you have the wave crest like this, the motion's actually perpendicular. So this is actually kind of a wave motion that's like this. So you can see how it's kind of incompressible, okay, because there's only shearing motion going on, okay? In fact, you can prove it. The div of this is 0 with a bit of calculus. So actually, you can do something else. You could take lots of terms like this and add them all up, and that's still going to be an incompressible flow. Okay, so I write a little bit of code in ShaderToy. You can see my little loop on the right that sums up over all these cosine functions. And I'm going to use kind of a method, kind of like what Stam described, to drag this checkerboard. And it flows something like this. So this is an incompressible flow. Each of those squares may get distorted, but they're staying the same size. And you can see how it's got a lot of fluidy stuff going on. It's got these vortices going on. But because I'm not using this to update the velocity, this is not a full fluid solver, all the vortices are staying in the same place. But if this was a full fluid solver, the vortices will all move as well, because the velocity would get affected every time. Okay? We can try the opposite as well. We can try, I can make the amplitudes parallel to the direction. So this would be like a wave with the crests are like this, and the velocities are like this. And you can see how this is basically compression, rarefaction. So this is the opposite of what we want. So a field like that would look like that. And then if you run that, so what happens is you get these flows. You can see there are points that are kind of sources, and there are points that are sinks, and you get flows going from the sources to the sinks. None of that vortex stuff. So incompressibility is crucial to getting these cool vortices. And you can kind of explain this a little bit better, actually. You see that function where the amplitude is equal to the direction? That's the gradient of another function, phi, which is the sine thing. Use some calculus, differentiate that, you get the one above. So these compressible things are all gradients of something else. And I can plot the gradient. It's basically this. It's not changing over time. So you can think of this as peaks and valleys where the bright whites are the peaks, the dark parts are the valleys, and the flow, well, it's going backwards here, but it's going from the valleys up to the peaks. So the peaks are the sinks, and the valleys are the sources. But the important thing is that the uninteresting flows are the gradients of something. And, well, we can do this for any kind of wave. So if you've got any kind of wave, any vector times a cosine, you can split the amplitude thing in the front into perpendicular and parallel parts, and you get one of these compressible flows, and you get an incompressible flow. But if you remember, Fourier taught us that any function can be written as a sum of a bunch of plane waves, a bunch of sine waves like this. So any function, you can write it as a sum of sine waves, split each of these sine waves up into compressible part and an incompressible part, and then reassemble them. So this gives a way to take any vector field that you have and just remove the compressible part and leave yourself with an incompressible field. And we can call this operation P for projection. And in fact, this is actually just a couple of lines of code, because you call the Fourier transform function, and that turns your function into a sum of all these sine waves. You then perform this projection operation and then do an inverse Fourier transform. So this is just a snippet from the paper showing this projection operation, and the thing on the right, on the second line, is basically some geometric algebra stuff, well, some dot products to compute the projection. So we're almost in a position now to start solving as I put these pieces together. This is part of the Navier-Stokes equation, okay? The velocity rate of change is given by this directional derivative minus the pressure force. So this is a derivation in Stam's paper, but it is standard stuff. You can apply this P operator to both sides. Well, if we're solving for incompressible flows, then the left is unaffected by the P. It's an incompressible flow, and the difference between incompressible flows is also going to be an incompressible flow. But on the right, well, one term is a gradient, and I've already pointed out that gradients give rise to these compressible flows, and that's what this P operation is designed to remove. So actually, that's what the equation simplifies to. This is now pretty much an algorithm. What this says is that we can take a velocity field on a grid. We can interpret this thing as saying, for some time, delta t, we can drag our velocities along using the dragging method. And then we do this projection thing. So what's happening here is that you have an incompressible flow to start with, but when you do this dragging operation, the advection operation, it might not be incompressible anymore. So we fix it by applying this projection. And that's pretty much a complete algorithm right there, actually. So this is how it's described in the paper. I've only dealt with 2 steps. I've colored them to see where they correspond to in the equation. Diffusion, again, is about viscosity. I'm ignoring that for the moment. And you can also add your own forces in if you like. Add in whatever forces you like and apply the projection step, and it ensures that the result is still incompressible. So here's some pictures from the actual paper. I'm not going to show actual video because you can just go on YouTube and find countless videos as I've showed you, so I can't add anything by producing videos of my own. But these are some images from the paper, and I can't tell you how excited we all were in 1999 to see this. Okay, so now move forward. I'll talk about some stuff that I worked on. This is quite a few years ago now, but very much inspired by some of these methods. But what I've described isn't enough to do like production scale fluid dynamics for movies. So here's one thing that's missing. So here's some fluid with some the kinds of things you expect to see in fluid, I guess. So these things provide boundaries. Okay, the fluid around here, we want it to match the velocity of the thing that's in there. But what I've described so far doesn't know anything about objects being in the scene, doesn't know anything about matching boundaries. So we somehow have to solve the previous problem, the Navier-Stokes equation, and somehow match boundaries as well. And if this thing's actually moving, you want to match the velocity vectors around the outside. And if it was spinning, you want to match those vectors too. So we have 2 problems to solve here. I can do it with a Venn diagram, right? I've told you all about these incompressible flows. You could also imagine there's a set of flows that have the correct boundary. That includes all kinds of crazy flows, the vectors pointing in all directions, as long as they have the correct thing along the boundary. And we want to find something that's in the intersection. And this is actually potentially a very difficult problem to solve, but there was a nice paper that has a beautifully simple solution to this. First, I'll make it more realistic. The intersection is actually really small. In fact, it might be 1 point. Okay. This method, okay, well, I'll tell you about the method generally afterwards. So there's a point up there that represents the current state that's neither of these things. And we want to move it towards the intersection. Okay, well, we know how to project onto the space of incompressible flows. That was the Fourier transform thing I described earlier. And you apply that, and it takes us there. So now it'd be cool if we could project onto the flows with correct boundary. Okay, well, there's a really easy way to do this. And it sounds ridiculous that this is a useful thing to do, but all you do is set the velocities along the boundary to be correct, and that's it. Ignore everything else. That's a projection step. In fact, in some sense, that's the closest velocity field to the one you started with that has the correct boundary conditions. So you can just do that. And amazingly, you can just keep doing this, and eventually it finds its way to the point in the middle. And this is great because you didn't have to understand. I mean, there's a gigantic literature on solving fluid equations with boundaries or whatever. You didn't have to understand any of that. You could just do this. It's so simple. I couldn't believe it. I mean, even though these are like billion-dimensional vectors, I mean, literally, right? If you're doing a fluid sim with thousands of cells in each direction, these are billion-dimensional vectors. It was like about 5 or 6 iterations, and it was like, oh, good enough. So it was great. So anyway, that's a paper. Oh yeah, one more iteration. Yeah. Eventually it arrives. So I got that from this paper. They call it iterated orthogonal projections. I'm not sure they realized that this was actually part of a more general scheme, because what I described was a very general algorithm that works for any kind of intersection problem with a convex set. Alternating projections is used all over the place. Electron microscopy, all kinds of weird mathematical problems. It's even useful for splitting optimization problems over multiple servers and then recombining the results. I mean, not exactly in this form, but that's a kernel of something. So I love that algorithm, and I would have talked about it if I could find a decent paper on it. But so, okay, I should mention viscosity. Bunch of molecules in a liquid moving around, bouncing all over the place. When two of them collide, if they have widely differing velocities, the chances are afterwards they're going to have more similar velocities in opposite directions, but, well, no, actually, no. Their velocities are going to be more similar. Okay? Typically what happens in a collision is they kind of share out the total energy between them. Okay? So this happens in a fluid. If you have one region of fluid with fluid going up, a region next to it going down, when these molecules interact, they tend to sort of cancel each other out and smooth out the differences. And so what viscosity does is if you have a vortex like this, over time it does spread out, but then it just fades away and you lose your vortices. So you don't want viscosity. In fact, I think the history of computer animation of fluids is pretty much a war against viscosity. And one of the reasons for this is that I've mentioned that you interpolate fluid at various points from the grid. Well, interpolations are just weighted averages of quantities. And every time you average, you're basically doing this smearing out process, just like the colliding molecules. So you don't want to interpolate, but the method requires you to interpolate. So you're introducing numerical viscosity, it's called, and that tends to kill off the vortices. So this is one problem with Stam's approach, is the vortices don't last as long as you want. There are ways to work around that. If you work at high enough resolution as well, you'll find the vortices do last for quite a long time. So, but I thought I'd mention like a modification that's very much in the style of Stam's paper that allows you to deal with that to some extent. I mean, this is just a picture from the paper. It's easy just to describe it. You can do the advection step that I described, run it forwards for a while, and then you get some new velocity field. And you think, well, there's probably going to be some error in there because of this interpolation business. So how can I find out how much error there was? Well, what you could do is basically flip all the vectors backwards and run the thing backwards again. You're not going to get to where you started from because there are errors from the interpolation. So you come back not quite where you started from, but you can look at the difference between the start and end, and that tells you how much error was accumulated. So if you guess that maybe half the error accumulated on the way out, you can just add that half difference onto the end. So that gives you a way of correcting to some extent. And this makes your vortices last a bit longer and it looks a bit prettier. So, and that's actually from this paper. Again, unconditionally stable. This is the big thing. It's more important to be stable for these kinds of things than to be accurate. So anyway, almost everything I've described here we used in a GPU solver called Plume when I worked at Industrial Light and Magic. There's one thing, we did try to use a Fourier transform-based method, but at the time we didn't quite trust NVIDIA's code that they provided for doing Fourier transforms on the GPU. So we actually used another method called multigrid, which actually has the same problem as the FFT method, that it can't deal with boundaries. So we used the trick I just described for dealing with those boundaries. So I'll show you some of the results we got. I can't take any credit for how beautiful the renders here look. I mean, the artists I work with, I just cannot believe they can produce images that look so good. So this is just some clips off YouTube. that I know are definitely use the tools I worked on. All of the dynamics, this is slow motion, but all of the dynamics here in anything fluid, fire, smoke, dust, explosions, this has all come from one of these solvers. In fact, there's actually multiple simulations going on in each of these. In some cases, I think in one shot there was like 80 different simulations, and then they're all composed together by the compositor. And all the interactions between the buildings and the fluid, that's all coming from this alternating projection algorithm. The resolution's not quite as high as I'd like, but it definitely works on an industrial scale. It probably still takes, I mean, to do one of these 3D simulations probably takes about an hour running on a GPU. At least it did 10 years ago. Today it's probably a little bit faster. But these are way bigger simulations than was originally done in '84. So. And we can also use it for things like just simulating air and making these droplets of water follow the air. It doesn't look that great from here at all, actually. But anyway, so there's a whole bunch of vortices and things that are forming, and this, you may recognize this from Star Trek. So I was pretty excited that they used my stuff on the Enterprise. So anyway, so I stopped working for Industrial Light and Magic and went and worked for Google X, in fact. And funnily enough, I found myself writing very similar code for some reason. So Project Loon, you may have heard about. It's basically a project to provide wireless over the world in remote places from balloons. It's a pretty crazy project, but that was the job, was to work on crazy projects at Google X. So one of the challenges here is, well, I mean, my colleagues were all having fun attaching Android phones to balloons and all this kind of stuff. But somebody had to do some theory, so I was actually the person who started the theory. So, and one of the problems was, if you've got a balloon at A and you want to get it to B, and the only thing you can do is change its altitude to catch different wind currents, what's the optimal path, what's the optimal choice of altitude that you should make? And so again, Lagrangian or Eulerian? Well, it seems like Lagrangian's a good approach because that's about particles floating in the wind or whatever, and that's what balloons are. But actually what you really want is to be able to give an instruction to every balloon at any moment in time, wherever it is in the world, telling it whether it should go up or down. So you want to build a big map for the entire world, saying up or down as a function of where you are and what the time is. And if you're going to make a map, it's going to be a grid. So you actually want to use an Eulerian approach. And it ends up that the planning involves solving a thing called the Hamilton-Jacobi-Bellman equation. And it turns out you can use a semi-Lagrangian approach. I'm not going to give you details about it, but it turns out this gives you a great method on a GPU for finding these paths. And it's weird writing almost the same code at one point as I'd written for a completely different job previously. So I don't know how I'm doing for time, but okay, so I should fast forward and mention some of the techniques people use today. So this is one popular approach. Instead of instantiating particles on a grid and then killing them, you could actually just have a bunch of particles and keep them going the whole time. But you still have to solve this pressure problem thing, which works well on a grid. So what you do is you transfer the velocities from the particles to the grid, then do that projection thing, and then transfer back to the particles. So that's called the pick method. But if you notice, it's got these two transfer operations that both involve interpolation. So that actually can kill your vortices again. So there's a little trick you can do, and there's variations of this, where you actually don't bring the velocities back from the grid, but you bring the changes that you made on the grid back to the particles. Or you can blend them in various ways or whatever. And this is actually, I think, maybe the primary method that's used these days. It works really well, produces fantastic quality results. Not a paper this time, that's in this book. Bridson is the key guy. Yeah. And then finally I'll mention the future. So I wonder if you can guess what's going to come up when I hit the space bar. Because of course it has to be a neural network, right? So I haven't really looked into this very closely. This is me just I've basically just read this paper. But basically, you can put in the input parameters from your simulation and do loads of simulations and train a neural network to replicate it. But there's something else actually that's quite interesting here. Generally, there's a technique there's a thing called a variational encoder using neural networks. Basically, you can take a fluid sim, or take your family of fluid sims, and you can find a reduced representation, a smaller number of numbers that describe it. In fact, the neural network can basically figure this representation out for itself and give you functions to convert from this latent space, it's called, which is reduced, to the original space. You can go back and forth. And so it's like a kind of magic where the neural network figures out a simplified way of doing fluid dynamics. And also, if you tweak a fluid dynamics sim in some random way, the chances are it's no longer a valid fluid dynamics sim because it's got random tweaks in it. But if you move to the latent space using the neural network function and then do random tweaks and then come back, you actually end up with a valid simulation as long as you trained it well and as long as your tweaks weren't too crazy. So this seems like a great possibility for creative input in the near future. So I don't know, that's speculative, but interesting times ahead. And I just want to finally just credit a couple of people. Well, Jos Stam, obviously. He's published papers that go way beyond the stuff I've talked about here. I haven't mentioned rendering. He's got papers on that as well. And my colleagues Olivier and Ian, who wrote Plume with me. And that's it.